Hello, and thanks for joining us in this episode. Today, we're diving into a fascinating piece of research about levitation at the microscale. Specifically, how tiny disks can float without touching anything, suspended purely by magnetic forces.
Yeah, it's pretty wild when you think about it. This technology, called micromachined inductive suspension, or MIS, opens up a whole world of possibilities, from frictionless microgyroscopes to micromotors and ultra-precise positioning systems. And all of this happens in a dust-free, wear-free environment.
Exactly. What's really exciting about this study is that it goes beyond just showing levitation. The researchers developed a detailed theoretical model that explains how stable levitation is actually achieved. And they combine that with a novel 3D coil design made using a clever wire bonding technique.
Right, so let's start by breaking down what a micromachined inductive suspension really is. At its core, it's a system that uses electromagnetic induction to levitate a tiny conductive object called the proof mass, or PM, without any physical contact.
And this proof mass is typically a small disk made of a conductive material like aluminum. The levitation happens because coils generate alternating magnetic fields, which induce currents in the PM. Those currents then create their own magnetic fields that push back, producing a repulsive force that lifts the disk.
The beauty here is that since there's no contact, there's no friction or mechanical wear. Plus, the system can operate in clean environments, which is crucial for sensitive applications.
Now, the big innovation in this paper is the use of two coaxial 3D solenoidal microcoils. These coils are made using an automatic wire bonder, a tool usually used to connect microchips. But here it's adapted to win tiny, precise 3D coils.
Yeah, that's a neat twist. Wire bonding lets them control the number of windings, the spacing between them, and the number of layers. The two coils share the same axis. The inner one is called the levitation coil, and the outer one is the stabilization coil.
And here's a key point. Both coils are driven by alternating currents that are 180 degrees out of phase. So when the levitation coil's current is at a peak, the stabilization coil's current is at a trough.
That phase difference is crucial. The levitation coil creates the upward force to lift the PM, while the stabilization coil provides a restoring force that keeps the PM centered and stable, kind of like an invisible magnetic bowl holding the disk in place.
The PM floats about 114 micrometers above the coils. That's roughly the thickness of a human hair. The levitation coil has a radius of about 1 millimeter, and the stabilization coil is almost twice that, around 1.9 millimeters. The levitation coil has 20 windings, and the stabilization coil has 12.
They also had to balance coil design with heat management. More layers means stronger magnetic fields, but also more heat and lower operating frequency. So they stuck with single-layer coils to avoid overheating and keep the frequency high, around 12 megahertz.
So how does this system actually work? The alternating current in the levitation coil creates a changing magnetic field, which induces eddy currents in the conductive PM.
Those eddy currents generate their own magnetic field that repels the coil's field, producing a force that lifts the PM. Meanwhile, the stabilization coil, with its current 180 degrees out of phase, creates a magnetic field that pulls the PM back toward the center if it moves sideways.
So together, they create a potential, an invisible magnetic bowl, where the PM can levitate stably without touching anything.
And because it's contactless, the PM can move freely without friction or wear, which is a huge advantage for precision devices.
Now, the researchers didn't stop at building this system. They developed a detailed linear analytical model to describe the dynamics of the PM near its equilibrium levitation point.
They used two coordinate frames, one fixed to the coils, called XYZ, and one attached to the PM, called XYZ. The PM's position is described by three generalized coordinates: lateral displacement, vertical displacement, and angular displacement, which is basically tilt.
The model takes into account the mutual inductance between the coils and the PM, the self-inductance of the PM, and the currents in the coils. The result is a set of equations that predict stiffness coefficients, basically how much force it takes to move the floating disk in each direction, and the conditions needed for stable levitation.
One important takeaway is that stable levitation only happens when the currents in the two coils are 180 degrees out of phase. If they're in phase, the system can't levitate stably.
The model also predicts a cross-stiffness term that links lateral displacement and angular tilt. This cross-stiffness limits the maximum levitation height, meaning the PM can only levitate stably up to a certain height before it becomes unstable.
That's a subtle but important insight. Now, to test their model, the team built a prototype and measured the stiffness coefficients experimentally.
They used a microforce sensing probe, capable of detecting forces as small as 5/1000ths of a newton and displacements as tiny as 5 nanometers. The PM was levitated at about 114 micrometers above the coils.
They applied controlled forces laterally and vertically, measuring how much the PM moved. Because of some geometric constraints, they measured angular stiffness indirectly by applying forces at 2 different points on the PM and solving for angular and vertical stiffness.
The results were pretty close to the model's predictions. Lateral stiffness was about 0.003 of a newton per meter. Vertical stiffness about 4.5 hundredths, and angular stiffness around 1.5 times 10 to the minus 8 newton meters per radian.
That's impressive agreement, especially given the tiny scales involved.
They also applied their model to a previously reported 2D MIS design, which used planar coils instead of 3D solenoids.
The 3D MIS prototype is about 10 times larger in linear dimensions than the 2D design. As expected, the 3D MIS showed stiffness values an order of magnitude higher in lateral and vertical directions, and 3 orders of magnitude higher in angular stiffness.
But interestingly, the lateral resonance frequency, which relates to how fast the PM can oscillate side to side, was similar in both designs, around 15 to 25 hertz.
So while the 3D MIS offers a larger stability domain and can handle bigger proof masses, it doesn't yet improve the maximum rotation speed for applications like micromotors.
The larger stability domain does give more flexibility in PM size and design, though.
Coming back to that cross-stiffness term, it couples lateral displacement and angular tilt, meaning if the PM tilts, it affects its lateral position and vice versa.
This cross-stiffness limits the maximum levitation height, matching experimental observations from previous studies.
They didn't measure cross-stiffness directly here due to experimental limitations, but it's clearly an important factor for future designs.
So what does all this mean going forward? This study fills a gap by providing a detailed theoretical model that matches experimental data, moving beyond purely experimental or qualitative studies.
The 3D MIS design with wire-bonded coils offers advantages in stability and coil design flexibility. But to achieve higher rotation speeds in micromotors or gyroscopes, the lateral stiffness needs to be increased.
Future designs might elevate the stabilization coil to the same height as the levitated PM to improve dynamics. The model provides general design rules to guide these improvements.
Overall, this research advances our understanding and practical realization of frictionless, contactless microscale suspensions, with potential applications in precision sensors and actuators.
To sum up, MIS uses electromagnetic induction to levitate tiny conductive masses without contact. The novel 3D MIS uses wire-bonded solenoidal coils with AC currents 180 degrees out of phase to achieve stable levitation.
Their detailed analytical model predicts the system's stiffness and stability conditions, confirmed by precise experiments. The 3D MIS offers a larger stability domain and higher stiffness than previous 2D designs, but similar lateral resonance frequency.
Cross-stiffness between lateral and angular displacements limits levitation height. Future designs aim to improve lateral stiffness to enable higher rotation speeds for micromotors and gyroscopes.
It's a fascinating step forward in microscale levitation technology, and I'm curious to see how these designs evolve.
Absolutely. Thanks for tuning in. We hope you found this as intriguing as we did.
Until next time, take care.